Okay, now that everybody can hear me? Yeah. Now that we know how to measure roughly how fast the code runs, we try to optimize it. We need to know how fast it runs in order to compare different versions of the code to decide which one is fastest. Of course, there are many other optimizations possible. I have some listed here. You have optimize for speed. That's mostly the most interesting, typically. User interactions, feedback, right? The phone, if you rotate your map with 2 fingers and it takes 10 seconds until the picture goes, you don't want to use it. So you want instant interactions to anything you do, even if it's a very, very complicated calculation behind the scenes. So you want to have that really snappy. Then for other problems, you want to perform calculation in a reasonable time, even if it's a very hard calculation. If you want to calculate the forecast for tomorrow and it takes 48 hours to calculate that, then it's not good, right? You want to have it faster. And sometimes you just want it done instead of waiting for infinite time. Other options is optimize for memory footprint. And on 32-bit LabVIEW, there is a hard boundary that you cannot exceed. So if you constantly get these out-of-memory errors, maybe you can change the code a little bit so you don't have that many duplicate data copies. In the worst case, you can go to 64-bit LabVIEW. Of course, other optimization is for code maintenance. You write clean code, keep it simple, don't have duplicate codes. Like if you have a diagram constant, that's it. The same in 5 different places, and you need to maintain the code and change it to a different number. If you need to change it in 5 different places, you might forget one. But if it's only one, wire to all the places where it's used, then it's much easier to maintain. So we just need to find the right mix, right? There's a balance. And if you ask a person what he has on his computer, what the computer can do, he can just quote something from the sales literature. Yeah, it's 4 gigahertz and has that much RAM, and has a big graphics card. But we don't really know what it can do with that, right? 20 years ago we had 100 megahertz Pentium, and that was really fast. And so comparatively, today's computers are supercomputers of the 1990s. So, yeah, we had a student long ago. He had a 40 megabyte hard drive in his old laptop. He bought a new laptop, had a gigabyte drive. 2 days later, he comes to me. He says, something's not right. It says the disk is full. He has just installed everything, all the clip art with the graphics program. He said, no, but it's a gigabyte. It cannot be full. So you have to understand the limits. Yeah. So we're in a very delimited sandbox where we can play with our data, right? As the, you don't have a laser pointer. Oh yeah. Which one? Oh yeah, okay. So it's easy to show it on a plot. That's the size, a log plot, because it covers so many orders of magnitude. Once the time gets too long, it's too slow. You can't really do it, right? And if the size gets too large, there are certain limits. So you hit the OS limit, and you need to go 64 higher. There are also certain steps here where you have the cache size, where if you go over that, it gets a little slower. But usually they don't really matter. And then for any algorithm, you can define a complexity, how the algorithm behaves as a function of data size, right? For example, an FFT goes with n log n. So it's a little steeper than a slope of 1 here on that graph. On a log graph, most things are quite linear. And for example, the slope of 2 means it goes with the square of the input size. The sum of an array goes with the number of elements. If you have twice as many elements, it takes twice as long. But there are other problems for example, a traveling salesman goes with the factorial of n. So if you have 5 cities, 3 million, you can easily calculate. But if you have 20 cities, you need an infinite time to do that. It's not doable. So this is our playground. We have to be aware of the boundaries. So what we want is, given n, typically the n is given by the problem, how big our arrays are. We want to go as fast as possible. Typically, you want to optimize from the inside out. See where most of the time is spent, and usually you have the inner loop there run the most, right? This might run 1,000 times more than out here. So if it's twice as slow out here, it doesn't really matter if all the time is spent in here. So focus, as a first step, focus on the innermost loops, the critical loop, and see how to optimize that. I mean, sometimes it's easier to do a for loop. You can calculate n, even if that takes a little longer, from the input sizes or whatever, instead of constantly asking, are we done yet? Do some comparison operations that might take time. So we go from the inside out and say, we focus on busy inner loops, make sure there are no controls and indicators in here, right? If that runs at a megahertz, nobody can follow that, and the user interface just interferes. And then we go look at primitives, pick the right primitives. I have examples for that. Then we look at array operations. And then as we build all these primitives and arrays into an algorithm, we try to find the most efficient algorithm to do a certain tasks. And then once we have all this together, we built an application that the user uses that hopefully functions very fast and is easy to use. So here we have a little quiz. A very simple calculation. I try to keep the examples very simple. Anybody can apply it to their own problems. For example, to calculate the distance as the radical of z squared plus y squared, you can calculate it like this. And these are big arrays, for example, 10 million, right? You have a big array, 2 big arrays, and you get an array out. You can calculate in many different ways, and 6 ways are shown here, A to F. And here are the scores. The fastest, if we say the fastest is 1, some are 9 times slower, some are 2.5 times slower, 2 times slower, and so on. And I wonder if any of you could guess in what order the speed is here. Which one is fastest? C. Okay. Which one is slowest? Okay. You guys don't know anything.
That's what you're talking.
Yeah. Okay, guess the order. This one's the slowest. It's 9 times slower. And this one also about 9 times slower. So they're almost, so at this point, right, we look at pattern. So for loop doesn't really matter. The next one is this. Okay. It's 2.5 times slower. And this is faster. And now the light bulb goes off, right? So, hey, if we wrap a for loop around it, we speed it up. Okay, so which one is faster here?
D is faster because you do the loop once.
No, D is slower.
You do the loop 4 times.
No, these are big arrays.
Doesn't matter. You go through array once.
Let's go through each element of the array.
Yeah, it does all the elements. These arrays are the same size. So this is the winner.
They're bigger complex
Yeah.
solutions.
Yeah, no,
Complex number solution.
that's right, but this takes less diagram space. It's easier to add. Yeah, if you only do on a scalar or something or a small array, it doesn't matter. It doesn't matter. I would use this. And many times you need the angle, so you use that anyway. So the question is, can we understand that? I mean, why does the for loop slow this down? Why does it speed this one up, right? And one thing is we can look at buffer allocations. If we do buffer allocations, anybody know that menu, right? What the profile show buffer allocations. We see little dots where buffers are allocated. And if you see here, this is completely in place, that the output buffer is reuses one of the input buffers, so there are no additional buffer allocations, right? And if you add a for loop, you just add a loop overhead, so we lose. There might be other benefits. This might better use like SOC instructions. These are instructions in the CPU where it can take several numbers at once and apply the same operation. I'm not familiar enough if that applies here. But here, there are two large buffer allocations. Here, it has to take the two large arrays and interlist them, right, to make the complex array. In memory, they're interlist. So it has to generate a huge array that's twice as long as these in terms of megabytes, right? And then it has to create a new array here, and that slows it down. But if you add a for loop, then there's only an allocation for a single complex element here. No longer we eliminate the allocation of that huge intermediary array. This is my interpretation. I might be completely wrong. But the numbers sort of would indicate that. On the other hand, this one, there are no visible buffer allocations, but the theta, the calculation of the angle, seems to be happening even if the output is disconnected. That's unlike that other example that Ed showed, right? So the compiler could actually be smarter and notice that this is not connected and speed up that function. So we can't really guess. Nobody had the right answer for all the owners. We really need to measure it. There's no way around it. So we look for array buffer allocations. And of course, many times, like the middle one where you go complex, maybe you can carry the data from the beginning as a complex array. So you don't need to allocate new complex array. And then that would be, again, faster. So maybe think about the data type way up from the beginning. And I call them vestigial loops. That's like your appendix, right? Doesn't have lost all its function. A loop that you can right-click and remove the loop and nothing changes in terms of function. That's one of those loops, but they do have an effect, right? They might reduce buffer allocations for temporary arrays, like the complex array, and different optimizations. In the future, the compiler could be tuned that the presence of the for loop is irrelevant, that it would pick the best solution, but I'm not sure how much artificial intelligence can go in there. So again, as if we also need data, now this is the fastest, right? Because if we need to calculate the angle separately, then we have to add more functionality here. But now they're actually very similar in speed. So that means this one is pretty good. It's similar to this, except if we don't need the data, we still calculate it, and that's a waste. Now quickly talk about array operations. Any arrays of any dimension require a contiguous space in memory. They're lined up as one line. They cannot be gaps. They cannot be split into two places in memory or anything. And LabVIEW is smart enough that it typically adds some slack space at the end, because, especially if the code indicates that it might grow in the future, if there's like a built array in there or insert into array. And often if the final size is known, it's always most efficient to allocate the final size and operate in place. Don't constantly grow the size. So if you have a 2D array here, I color-coded it a little bit. In memory, it looks like that. Doesn't matter what the data type is. Strings are slightly different. But now, if we insert a column in memory, only the first row can stay where it is. All the others have to shift up, and the new column has to be interlaced, right? And if we still have room, this is still relatively cheap. But if we run out of space, if it exceeds the allocated size, then LabVIEW has to grab everything, request a larger space, move everything over there, and can continue from there. On the other hand, if we append a row, most of the elements can stay in place, and only a few are added, again, until we run out of contiguous space, and we have to do something about it. So it's always best to operate on fixed size arrays. So as an example, I wrote 4 different codes to do an endpoint running average. It's very simple. It's an array, right? It has to keep the last endpoints and average them. There's a stock mean point by point. There's a build strip. Start with an empty array in a shift register. Prepend new elements until the size is reached, and then trim back if it gets too big. So always add a new at the beginning and cut the one at the end. In places, have a full allocate the full size and always replace the oldest with the newest, just going through it and average that one. And there's an efficient way. It's the same as in place, but in addition, we keep also the sum in a shift register, where we just add the newest value and subtract the oldest value. It's very simple. It's much faster than do some huge array. And so, we don't need to start some large arrays. Let me get that thing.
There's one more way to do it.
Yeah.
If I can add to it, if you do an array shift.
Yes.
Shift the array. If there's no reallocation.
Rotate, you mean?
Yeah, rotate.
Rotate array. There's no new allocation, but you have to touch every single element.
It's not. You don't take a hit. For some reason, you don't take a hit. So we've done that. We've done some benchmarking.
No, it's possible that LabVIEW just remembers the start index and leaves them in place, or something the compiler does. But the mean point by point actually rotates, and we can look at the benchmark.
So anyway, I didn't throw out.
Yeah, no, that's true.
As an additional benchmark, I gave you to see
Yeah.
compared.
No, I'm not giving the final solutions here. I'm just giving ways to look at things, right?
Sure.
And it's important that you look at all your problems yourself and code it up. If you're interested, code up any other variation and see if it's faster, slower, and all that. There's no way to say what's faster unless you try it.
Right.
But that's a good idea. The rotate is. I'm not sure if it's really as fast as it is. Okay.
Yeah. The other thing is just protect your efficient against NAN. Because if you have NAN in the chain,
But that's only in 32-bit LabVIEW. 64-bit handles it much better. It's a problem with the Intel compiler.
Well,
if there's an NAN in the array.
If you keep the sum and you add NAN, and your sum goes to NAN,
Yeah.
and then when you
then it gets stuck.
So
That's right. Yeah.
So.
Yes, but you don't want to average if it's NAN, so you might want to just exclude that from the beginning.
Right.
Yeah. Okay. So many projects open here. Okay. So here I have running averages, and you see the average. For this is for 20 elements, they're all about the same speed, right? But if we go, this is a little hard over the shoulder. If we go to like 100K elements, that green light goes on when it's what? Okay. Okay. Where is the mouse? I don't see the mouse. Okay. Yeah. So if we do 100K, we have to wait until all of them are green. Then now you see that this is like, it's getting 1,000 times slower than the efficient version, and so on. And so I have the graph here. Let's just look at the graph. Or you can quickly look at the code. That would be nicer. Yeah, the LabVIEW audience here. So, yeah, here. So this is a different style benchmark. I have a 64-bit counter here, and I just run these loops as fast as they can. Typically, they're in disabled structures only look at one. I run all at once, so the results are a little biased. And at slow intervals, like every half seconds or so, I just read out all the iterations, and that tells me how many times they spun during that time interval. Right, this kind of VI you can't really test well like the other way with the tick counts, because it's sort of a continuous thing. But so the top you have the point-by-point mean. Here you add the random number, right? And if it's larger, you trim it back. You take the mean. Here you have a fixed size array for the endpoint average. And with the quote in the reminder, you just go through the points in sequence and start over and replace the oldest. And here we have that second shift register where we subtract the oldest that we get out here and add the newest to the current sum. And now we only need to divide by the size, by the valid size. And yeah, so these are all posted, so you can study them in detail. I don't think it's worth going in there. And you can also email me if you have questions. But if you now look at the details here, these are the times. And what's amazing is, so these go relatively flat initially, and that's because all the overhead is relatively constant, the random number generation, the size, and all that. So these are sort of flat, but at one point, the summing of the array element takes over, which is, of course, with a complexity of n, so the slope should be 1 in the log-log plot, and it sort of is, right? Yeah, it goes from here to here. But if you now look at the stock, it's sort of good, it goes up. Of course, because of the sum. The build strip is clearly slower than all the other ones. And I wasn't patient enough to measure up here. The in place is a little smoother than the stock. And if you look at the efficient, even if you have 10 million elements, it's 140 nanoseconds or so. It's completely independent. So the size of that array doesn't really matter. Right? The main operation is the add and subtract, and this is just a few numbers. It's totally cheap, and it doesn't change. And so one thing with the stock is that it's really, really fast. It's as fast as this one until the buffer fills up, and then it gets as slow as this. So there's possibly improvements possible. It's the mouse.
I think the stock isn't protected against NAN, which is why it has to go slow.
It does other things. For example, I think you can change the size during the run. So it's a little more flexible. Yeah. But I think there would be better ways to do it. Resume slideshow. Okay. So stock is easy to use, fully tested, can change n, and once n is reached, it slows dramatically if the sizes are very large. It does that rotation. The code is open. You can look at it. It does a rotation and so on. And before the size is reached, it actually does something very similar, where it only takes subtracts and adds. So the build strip is also fine for small n. Simple code. The resizing is expensive, and the fuller it gets, the slower it is. So that's a sort of unpredictable. You test it quickly, it runs fine. You come back from lunch, and suddenly it's really slow. The in place is good, better than stock once n is reached, and but it has a very constant speed. It's always the same speed for a given size, and the speed is constant, even independent of size, and that's O1 complexity. How are we going to time? When is it over? Okay, 10 minutes. Okay, so this is Ed showed one of those. I did 5 different algorithms, and again, they're available online. Maybe I don't show the code. You can study it. The DOM algorithm, which takes a number, and then starting with 2, it tries to divide all of them, and if all of them don't succeed, it knows it's a prime, it adds it to the sum. And simple is divide the current number by all found primes in order, and append to the list of primes, and add to the sum if a prime is found. We can only calculate at the sum of primes, which has to be a 64-bit integer because it gets very big. The very known algorithm from very long ago. There's a newer one which uses a slightly smaller table for the indices, and I made a variation in order so it calculates the Boolean array first once, and then keeps that in memory, and then after that it can run up. It's really fast. And of course, what you can do, you can recalculate all the numbers, all the possible outcomes, right? But then you run out of memory, and so yeah, I'm not going to show the demo. But so I made a VI. You click on any of these buttons, and it doubles the size until it takes more than 2 seconds, or it reaches the 2 to the 28 size. And if you look here, so this one goes really steep, and if you look at the slope, it's 2. That means the doubling cost, if you double the size, it's 4 times slower, right? The simple one is a little faster, because as soon as a division succeeds, we bail out, and many times that filter occurs very early on, so we don't go with the square. The Eratosthenes goes with 1.12, and that's very close to the value of n log n, which is the theoretical value. And the Sundaram is 1, is a slope of 1, because it's really linear the way it's implemented, and it's really fast. And yeah, if I would show if you look at that VI later, you run all those, you can move that cursor to anywhere you want, and it tells you what the extrapolated speed length of time is for that cursor. So I have it at 100 million, and you see the DOM uses 40 weeks, right? And then the simple uses 8 hours, the retosted uses like 2 seconds, and the Sundaram takes like 1/10 of a second. So very simple differences, small differences in code can have a huge impact. And you should always be aware of the scaling. You know, the steeper that curve is, the more dangerous it gets, because I guarantee you, you write a program, your users will throw 100 times more data at it, and then you somehow need to deal with it. So the DOM is fine for small n, simple code, optimized for very limited hardware. If you need to run it on your lunar lander computer that has only like 2K of memory, you cannot store the list of primes, right? You would have to do that. And it takes no space, there are no arrays involved, right? And the simplest is faster. Retosted is even faster and uses 256 megabytes of Boolean array for the lookup. And the Sundaram uses half that because it only has the odd elements in that lookup array. And the cache version is even faster. If you don't cache that, it's actually slightly slower than this because it needs to do more complicated calculation. And the direct lookup table is instantaneous, but yeah, it's not good. It's maybe in 10 years, everything is 128-bit processors and things like that. Yeah. Now we talk about optimizing for memory. The data size is often given by the problem, so we cannot reduce it, right? So we just want to make sure we eliminate extra memory copies. Avoid indicators, local variables, value property nodes. All these have extra buffers. Make sure the panels of the sub-VIs is closed. Disable debugging. If you have non-redundant sub-VIs, they reuse memory. So if you keep calling with about the same amount of memory, they hold on to that and reuse it, and it's very efficient. Make sure you use efficient structure. Data value references works well. Action engine also shares stores. That's the same as non-reentrant. Or you, in the worst case, you have to go to 64-bit with all the disadvantages of 2-bit support. Watch for memory leaks. LabVIEW is typically very good managing memory, but poor coding can cause bombs. You don't grow for arrays forever unchecked, right, and let it run for days. Or if you, like, it's well known, if you constantly open references and without ever closing them, you run out of memory at one point. There's a desktop execution trace toolkit that allows you to analyze exactly when the allocations occur, but usually you don't really need that if the code is well written. There's a function request the allocation function, and that's really the solution. For example, if you have like a non-redundant sub-VI and you put that in there, then whenever the sub-VI ends, right, it will deallocate the memory and you call it a nanosecond later with the same array size, it needs to request it again. Yes?
I just wanted to share, I asked one of the NI employees about this, and they said there's a toolkit that was released in, I think, 2014 SB1. It's called the Deallocation Toolkit. Okay. And it'll give you thresholds, so you can actually watch the eyes grow to check your memory. So it's another tool that
Oh, okay. That's not this?
No, it's not the toolkit. It's not the execution trace toolkit.
Okay. Yeah, I'm not aware of it. Yeah,
I wasn't even until yesterday.
Okay.
So I just want just sharing.
Okay, thank you. So my advice is focus on speed optimization. If the VI is fast, it most likely won't run out of memory that quickly, unless you do something weird. So I have a few, yeah, if like 5 minutes, and talk a little bit about my research. We do EPR spectroscopy. We attach little molecules to big proteins, and if we do it right, we can attach two at well-known places, and we can put that in a spectrometer, and we can measure the distance by EPR spectroscopy. We can also look at dynamics. I'm not going to go into that. That's a different program that I mentioned a couple of years ago. So basically what we get, we manipulate the electron spins with high-power nanosecond RF pulses at about 35 gigahertz, and we get a resulting echo modulation that's a cosine of the pulse separation and all 11. I won't go into it. It's a LabVIEW thing right here. So basically, if you have a given distance, you get a certain oscillations. If you have distribution of distance, it's a damped oscillation. Let me go back again. So if you have a close distance, it's a high frequency, and it's not a cosine. It's a complicated weighted sum, because it needs to integrate over all possible orientations. So we measure this, and we need to calculate this. It's easy once you have this to calculate down here, but we need to solve the inverse problem and given a dipolar signal. So this is a relatively complicated function to calculate. If you look at the peak function is a bad function because it has two peaks that are infinitely high but infinitely narrow. So the area is still finite. And so we typically have to do it numerically. And I show you the program later. And so it takes like to calculate one trice at high resolution takes like 40 milliseconds, and then we need like 200 to do the calculation to form the matrix. So it would take 10 seconds. But what I do is I calculated very high resolution with 16,000 points. And then all you need to do is index into it and interpolate, right, to derive all the other functions for all other distances and offsets. And you just give it a fractional index and you get a value back. And that's now typically solved in sub-milliseconds. And so it creates that huge matrix, right? I show the program as a last thing. And I just added a little indicator that looks in the registry for the CPU frequency, and then calculates how many CPU cycles it takes per array element. Remember, it has to take two values, interpolate all that, and it takes it like 31 cycles, it shows here, right? So I don't think you can do it in 3, so a factor of 10 speed up is probably not possible. I'm happy with the 31, and it's faster than all the other killer calculations I have to do later, like the regularization. And so the kernel calculation is 10,000 times faster using that lookup table, and it's easily within 10 to the minus 8, much better than the noise in the data and all that. And so I can instantly show in real time, I can move a cursor and instantly recalculates, and I see exactly what I'm doing. I don't have to wait for it. And it has to do all this. So, and then I do highly optimized inner code. I solve it. I have to do the real distance distribution. I calculate it's a Levenberg-Warburg fit with 200 variables, and that takes only seconds. And the UI is always fully interactive. And I think, okay. So this is the result in 2008. That was much harder back then. Now the program, I have to program it, it's much easier. But we measured all these distances in the visual receptor of the eye, rhodopsin, right? You measure it in the dark, and the crystal structure in the dark is known, and all the distances agree exactly. If you take that crystal, you shine light on it, it falls apart, so you cannot do the structure. They can do it now with other methods, but back then we did that. We shine light on it, and you measure all the distances, and you see this one moves out, and this has now been verified by many other labs. But this was sort of the first time where we actually measured what the structural rearrangement is that triggers the visual cascade of the signal transduction, right? That you actually, at the end, you have a whole impulse going into the brain that tells you that there is light somewhere. And I talked about that last time. So I'm not going to show that. Just a result. This was highly parallelized code where I do fitting of the line shapes, and recently some guy in Germany had a 48 CPU machine, and if you just let it run on one CPU core, right, then they're all pretty crappy. The atom is almost nothing, right? This is slower because it's lower gigahertz. But if we allow it on all things, it fully scales up and uses every single CPU core at 100%. And you can still watch a video or use some other programming. It doesn't slow down the computer, it just does that. And yeah, 100% CPU on all the cores. This is my machine. This is the 32 core. So a quick summary. Yeah, so you should put benchmarks in all the programs and encourage your users to report back. And I have a little code that lists the CPU characteristics, the amount of memory, plus the results of the benchmark, and a button to copy it to the clipboard, they paste it in an email, send it to me, and I put it in a list. I maintain it on my website. So document the behavior, make sure it scales well, it doesn't blow up when the arrays get a little bigger. But as a final note, the correct result is still more important than speed. So if it's really fast and it's wrong, it's not good. So now one little quiz. On Monday, I was in the academic forum up there, and there was a poster, and I took a picture with my camera. Let's see. I mean, after a while, you develop an eye for these things. Let's see what's wrong with this code, right? So he takes the number of virtual CPUs here and parallelizes the outer loop. And inside of each parallel instance, he parallelizes the inner loop, right? So what's going to happen there? It's probably not good, right? Unless the compiler protects against that in some way. Huh? No, it doesn't. It doesn't. You just get a huge washing machine of things, right? Shuffle things around. I don't know. I mean, some people say, oh, parallel is faster, so let's parallelize everything, right? You really need to benchmark it.
Parallelize
Probably, yeah. Yeah. No, I mean, you just need to benchmark this. Yeah.
I realize that my code is running twice as slow.
Yeah, it doesn't do that, right? Yeah.
But it does do better if you back off stuff with all you have available.
Yeah.
If you mess them like that, you get to the state where you allocate all, and it actually runs a little slower than you get an 8, you pick 6.
Yeah.
Or if you have 2 of these, you pick 2 or maybe 3. That works pretty good. You pick that 3. If you do the other one, you actually start to.
Yeah, if you only have one parallel loop, then you're fine. You can use
It's not
all
terrible,
of
but
the
it's certainly not optimal.
Yeah. So other things. Anybody recognize anything else? Look, this is a scalar going in. They do the innermost loop. They calculate the sine and cosine n times m times. Of course, most likely the compiler might actually move it out as loop invariant code, but I wouldn't trust it. So we have this, right? Only parallelize the outer loop, if any. This is so little, so it might not even be parallelization overhead, might even cost more. And there's also a function that does the sine and cosine in once, and since they're mathematically related, it's much cheaper, right? Instead of doing separately. And again, this should be moved out of the loop, right? Because it needs to be done only one. Even if the compiler optimizes it, it should be outside, just for clarity. So this is just a bonus thing, a slide I made last night.
All right. Well, we will have time to hang out. It's the end of the day, but I want to make sure while the room is full that we thank the speakers with the applause. Yes, so the track is officially over, but we still have time to hang out if you have a few more questions for the Jedi Master here. That's funny.